Hello, my name is Mick.
My name is Avery White.
My name is Megan Kleinheinz.
My name is Lauren Kaus.
I'm Cameron Czubay.
Our project is the development of a Thorax simulator for the testing of sleep apnea treatment devices. We are Senior Design Team 1 with the Biomedical Engineering Department, and our sponsor is Biomedical.
So some background information on our project. Sleep apnea is a disorder that inhibits a patient's ability to breathe while sleeping. The tongue relaxes back into the throat, closing the airway and interrupting breathing. These interruptions in breathing can lead to various negative health effects that can impact a patient's day-to-day living. To resolve this, Biomedical is creating novel medical devices that can treat sleep apnea patients. These devices are called implantable pulse generators, or IPGs. Similar to how a pacemaker pulses for the heart's motion, Lunair's IPG sends a pulse to the tongue, preventing it from blocking the airway. As patient testing can be time-consuming and expensive, there is a need for a Thorax testing model to verify the effectiveness of IPGs throughout the design process. Our goal is to provide an electromechanical test model that can replicate the motion of the chest seen during respiration for IPG testing.
So here's our proposed solution to the problem statement. This design features a sensor and our 3 servo motors to achieve accurate movement with 3 degrees of freedom. On the top of our model is a sensor with an accelerometer, gyroscope, and magnetometer. Our Arduino IDE script controls the servo motors through the Arduino Uno. And then we have created a basic server with Python to communicate with IDE to store and process data.
There are 2 distinct sections of the mechanical design, the pan-tilt element and then the linear actuator. For the pan-tilt element, there are 2 servo motors driving the motion. The top servo tilts our sensors, and the bottom servo yaws our sensors. The motion of breathing also incorporates vertical motion. A linear actuator is used to move the pan-tilt model in the Z direction. These motors and actuator are guided by a feedback system with a sensor. This is achieved using a PID controller. After translating the IMU data to position, the PID controller continuously tracks the error between measured and expected position. It then sends feedback to the motors to correct the error, allowing it to trace an imputed waveform.
We were able to track the motion from an input waveform, and from testing, our error bounds fall within 10% about 20% of the time for tilt and up to 80% of the time for yaw. For our next steps, during verification testing, our motor controller for our linear actuator was damaged, so a replacement needs to be purchased. For some future work or changes for improvement, there is still room for error reduction. Some ways to achieve this are adding servo motors with a higher step resolution, replacing the current wiring setup with a permanent soldered circuit or PCB, and through noise reduction with a more stable vertical platform. Additionally, the sponsor provided an impedance circuit that still needs to be integrated with the design.
To wrap up, we would like to say thank you to our advisors, Dr. Orhan Soykan and Dr. Bruce P. Lee. And of course, a big thank you to our sponsors at Biomedical. Thank you, Kurt Berquist, Dan Trost, and Christine Hewitt for your guidance throughout this project.